right, so in this lesson, we are going to look at graphing cosecant and secant functions that have period changes and phase shifts. They can also have other transformations also, but those are the only two that are given names. One of the things we've already learned is that the cosecant function is the reciprocal function for sine. That cosecant is equal to 1 over or divided by sine of x. And so the graphs of those two are related by that reciprocal relationship. So here we can see that the zeros of our sine function correspond to the vertical asymptotes of our cosecant function. So sine has a 0 at 0, 0. That 1 over 0 creates an undefined ratio, which then creates a vertical asymptote for the cosecant function. Sine is also 0 at pi and at 2 pi, so we can see those would also create an undefined ratio, 1 over divided by 0, which creates vertical asymptotes there. So one of the things we need to understand is that these two pieces right here of the cosecant curve, which are in blue, they are the first cycle of our cosecant function. And so the relative maximum here at pi halves comma 1 becomes a minimum of this U-shaped curve that approaches the asymptotes. And the relative minimum of sine at 3 pi halves comma negative 1 becomes a relative maximum of the U-shaped cosecant curve here. So since this is one full period from 0 to 2 pi of sine, both of these U-shaped curves create a full period of our cosecant function. So that means that the period of our cosecant function is 2 pi radians, unless it gets changed by the parameter of 1 over b. We are going to have those asymptotes. So in one full cycle, one complete cycle from asymptote, we actually have 3 asymptotes because there are 3 zeros or intercept midline points for sine. So it creates 3 asymptotes in a full cycle of our cosecant function. And so the domain of the cosecant function is not the set of all real numbers. It excludes the values that create the asymptotes. The range is from negative infinity to the maximum value here of negative 1, and then from 1 up to positive infinity. So it excludes, there's nothing in this middle section for cosecant. Looking over here at the table, the pi fourths radians, when you do sine of pi fourths, you get root 2 over 2. And so the reciprocal of that is the cosecant value. This decimal is the decimal approximation for the square root of 2, which is the reciprocal of 1 over root 2 over 2. So this is your decimal approximation for the square root of 2. And this is, again, your square root of 2. This is your negative square root of 2, which are all the reciprocals of your root 2 over 2 and negative root 2 over 2. And that's what these points are. That's your root 2 and negative root 2 values. And then these are your relative maximums and minimums of the sine function, becoming the opposites for your cosecant function. All right, let's take a look at what we have to do graph. So here we're looking at the structure of our cosecant function and our secant function with all of the parameters in place. The period of a cosecant or secant function is calculated the same way as it is for sine or cosine because they are reciprocals of one another. So we have our 2 pi radians, which is our period for the parent function, divided by the positive value of our 1 over b parameter. And then we have our phase shift, which again is done the same for all trigonometric functions, c divided by our 1 over b parameter. There are a couple of different ways that we can graph secant and cosecant. One, we can use this function itself. Some people also like to use another strategy where they lightly graph the sine or cosine curve that's related to it first, and then they invert everything to create the asymptotes and the curves of secant or cosecant. It can be done both ways. All right, let's look at this example. So we're going to specifically identify the period and the phase shift, but A does affect things. It's just not an amplitude. There's no amplitude for secant or cosecant. It does still create, in this case, a vertical stretch, though, by a factor of 2. So here I'm looking at the 2 would be my A parameter. The 1, the coefficient of x, which is a 1, that's our 1 over b parameter. The opposite of this positive pi fourths, that, remember, is what we call c. And then k is 0, which in this case we can see isn't there. So the period of the function here that we're looking at, we're going to have 2 pi divided by our 1 over b parameter, which is 1. So the period of this function is going to be 2 pi radians, just like the parent function of cosecant. We do, however, have a phase shift. So it's c divided by 1 over b. So remember, we have to take the opposite of this positive pi fourths. So that would be negative pi fourths. And then divided by the 1 over b value of 1. That gives us negative pi fourths. And so that being negative, that means we have the horizontal translation to the left. So this is going to shift everything left pi fourths units. All right, so on this lesson, we've been given graphs that have the axes and the scales already fixed for us. It's actually a pi fourths scale that we're looking at here because we have these lines in between 0 and pi, so it divides it into 4 pieces. We've got a pi fourths scale, which should work nicely for our problems. And then we've got basically kind of a half unit scale here, with this being a half and then 1 and 1 1/2 and 2 and so on and so forth for y. All right, so let's take a look at this. So one of the things that we want to do is figure out where our asymptotes are. And the asymptotes are going to be located where sine would be 0, because the reciprocal of 0 is 1 over 0, which is undefined. So a good way, instead of just graphing the sine function, is just to start with your sine function and where it is 0. So we know that sine starts at 0, 0. That's going to turn into an asymptote. But that asymptote is going to be affected by our phase shift. So its location has to shift left pi 4 units. And so the asymptote that would have been the y-axis shifts to pi fourths units, and it's going to be right here. Your asymptotes have to be graphed, always, for secant and cosecant, and they have to be graphed as dashed lines, no exceptions. I guess there's one exception. If you have an asymptote on the y-axis, you don't have to put a dashed line there, but everywhere else you have to. It's not like the midline where you can graph it or not, depending on if you want to. Asymptotes have to be graphed. All right, so now what we know is that this is the beginning of our first cycle in this case for this cosecant function. The period is 2 pi radians. So 2 pi radians later, we're going to end the first cycle with another asymptote. And so, again, I can look at it, well, I've got 8 squares for 2 pi, or I can take my negative 1/4 pi and add 2 pi to it. Either way, I'm going to end up right here at, that's 5 pi fourths. No, 7 pi fourths. Right there. We also have to understand that just like sine has 2 midline points, or between it, these would be midline points here and here for sine. There's a third midline point exactly halfway between. Therefore, there's a third asymptote exactly between these two asymptotes. So that would be 4 squares over. All right, so now what we've got for the pieces of the curve. So for the pieces of the curve, I'm looking at, I have to realize that my A value of 2, that's telling me I have a vertical stretch that I have to graph. And so now I'm going back to sine again. So what I'm looking at here is my sine function. My sine function from its first midline point, which here becomes an asymptote for cosecant, from there it goes to a relative maximum at 0, 1. So that maximum is going to occur halfway between these two asymptotes, and it's going to be stretched by that factor of 2. So now it's 2 units above y equals 0, which is our k value because we don't have any vertical shift. and it becomes a relative minimum for this piece of cosecant. So cosecant, what's happening then is that now we can draw in the U-shaped curve here. So you'll notice I didn't worry about any other points, and that's okay here. We are sketching as much of the function as we can, so the key thing is to understand where your asymptotes are, where your relative minimums and maximums are, and then show each curve going towards your asymptotes correctly. So for the next one, for sine, we have a relative minimum here. That relative minimum would have been at a y value of -1. So it's going to be stretched to 2 units below the x-axis and become a relative maximum for this part of the cosecant curve. And so this is one full cycle. One up u and one down u creates one full cycle of the cosecant curve. So now what we're going to do is extend this. All right, so I'm going to add up my other asymptotes. So what I'm looking at is basically every 4 squares, I'm going to find an asymptote. So I go up another 4 squares, I've got another asymptote. Another 4 squares, another asymptote. I'm graphing as much of this function as I possibly can on this given graph. And to the left, moving 4 squares over each time gives me asymptotes. All right, and then our curves alternate. So if I'm moving to the right, this is a relative maximum curve, so it bounces back up and does another relative minimum curve. Then it bounces down and does another relative maximum. Bounces back up. Now, to graph as much as we can actually graph a little bit. We can actually graph half of one of our curves over here, because 2 squares over, I would actually have another relative maximum, and that piece looks like that. Moving to the left, I have this relative minimum piece, so it's going to bounce down to a relative maximum. Bounce up to its relative minimum piece. That's not a good curve at all. Bounce back down, and so on. And then this piece we can graph the whole thing with the space that we've got. All right, and that would create a decent sketch of this cosecant curve or function. All right, we're going to end this video here. The second example will be on the next video.